Hello and welcome everyone. Thanks for joining me today. I'm Benjamin, part of the technical and engineering team at Ventuer. My own background is in architectural design and building science, and I've spent more than 2 decades working across commercial buildings, design-intensive projects, complex facades, and some unusual projects that sat right on the boundary between architecture and hard engineering. In this session, we're going to focus specifically on weather louvers, not as facade elements, not as architectural detailing, and not as part of a wider building aesthetic, but purely as engineered systems designed to manage airflow and water simultaneously. When we remove the architectural context, what we are left with is a device that has one job: to allow air to pass through freely while preventing water from doing the same. So the intent of this session is to step away from where louvers sit in a building and instead look closely at how they actually function, the physics behind them, how they are tested, and what really defines performance when they are exposed to real weather conditions. Over the next 20 minutes or so, we'll build a structured understanding of how weather louvers behave as systems. We'll start with the fundamentals of how air and water behave differently, because that difference is the fundamental basis of louver design. From there, we'll look at how wind-driven rain behaves in real environments and why that is very different to simple vertical rainfall assumptions. We'll then move into blade geometry, how shape, spacing, depth and orientation directly influence both airflow and water capture. After that, we'll cover testing and what standards exist, what they actually measure, and how to interpret those results correctly. And finally, we'll bring it all together by looking at real-world limitations, where these systems perform well and where they begin to fail. The focus throughout is on performance as a system, not as a product. A weather louver can be described very simply as an opening that allows air in while keeping water out. But that definition hides what is actually happening. In reality, the weather louver is a passive separation device. It must do 3 things at the same time, without any moving parts. It must allow airflow to enter and change direction multiple times. It must prevent water droplets from following that same airflow path. And it must manage any water that does enter by capturing it and directing it safely away. So rather than being a simple grill or cover, it is closer to a fluid management system, where air and water are being deliberately separated through geometry and physics. When you look at it this way, the simplicity disappears, and what remains is a highly engineered aerodynamic device. One of the biggest challenges with weather louvers is that performance is not intuitive. 2 systems can look almost identical from the outside. Same blade spacing, same frame depth, similar appearance, and yet perform completely differently under test conditions. And that's because what matters is not what you see, but what happens inside the system. Performance is driven by airflow behavior, droplet momentum, blade interaction angles, internal pressure zones, and drainage pathways. None of that is visible externally, so relying on appearance is misleading. In fact, one of the most common misconceptions in facade design is assuming that similar-looking louvers will behave similarly. In reality, small geometric differences can produce very large performance differences. At the core of all weather louver design is a simple principle. Air behaves like a fluid with very low inertia. Water behaves like a fluid with significant mass and momentum. Air will follow pressure gradients and change direction easily. Water droplets resist that change. They carry momentum in a straight line until something forces them to deviate. Weather louvers are essentially designed around exploiting this difference. If you can make air turn, but water continues straight or impact the surface, you can begin separating the 2. That is the entire foundation of the system. At a slightly deeper level, the behavior we're seeing inside a weather louver is governed by 2 dominant forces: drag and inertia. Airflow is primarily influenced by pressure and drag forces. because air has very low density, it responds quickly to changes in pressure and will follow curved paths with relatively little resistance. When the geometry of a louver forces the air to turn, the air simply follows. Water droplets behave very differently. They are governed more directly by inertia. Once they are moving, they resist changes in direction and they will continue along their original trajectory unless a sufficient force is applied to redirect them. So what the louver is really doing is creating a situation where drag dominates for air, but inertia dominates for water. That difference is what allows separation to occur. In real weather conditions, rain really falls vertically. Once wind is involved, droplets are accelerated horizontally, often at significant speeds depending on exposure and building height. So by the time rain reaches a facade, it is not simply falling, it is moving with combined vertical and horizontal velocity components. This is critical because it means water is arriving with momentum in a specific direction. And that direction is often aligned with airflow paths through the louver. So instead of dealing with a simple gravity-driven water, we are dealing with kinetic, wind-driven droplets that behave very differently under deflection. An important factor that often gets overlooked is droplet size. Not all rain behaves the same way. Larger droplets carry more mass and therefore more momentum, which makes them more likely to continue in a straight line and impact the blade surface. These are generally easier to capture. Smaller droplets, however, are much more easily influenced by airflow. They can follow air paths through the louver more closely and are therefore more difficult to separate. So when we talk about performance, we're not just talking about how much rain there is, but also the nature of that rain, whether it's made up of large, heavy droplets or fine, wind-driven mist. When air passes through a louver, it is forced to change direction. Air follows that path relatively easily, but water droplets behave differently. Unless they are forced to impact the surface, they tend to continue in their original trajectory due to inertia. So inside a louver, a separation effect begins to occur. Air turns and flows through the geometry. Water continues forward until it either impacts a blade or passes through gaps. This difference in behavior is what makes separation possible, but only if the geometry is designed to exploit it. For a louver to actually work, droplets must be forced to interact with blade surfaces. That interaction is called impingement. When a droplet impacts a surface, several things happen simultaneously. Its momentum is reduced. It spreads into a film or smaller droplets, and it becomes available for capture and drainage. Without impingement, there is no mechanism for separation. So blade design is not just about airflow, it is about ensuring that droplets are intercepted at predictable points in the system. If we think about this as a system, what the louver is actually trying to achieve is separation efficiency. In simple terms, that means increasing the probability that water droplets will deviate from the airflow path and be removed from the airstream before they pass through the opening. Every part of the louver contributes to this. Blade shape, spacing, depth, and internal drainage, all of it is working towards the same outcome, maximizing the number of droplets that are intercepted and captured. It's not a binary condition where water is either stopped or not. It's a probabilistic system where performance improves as separation efficiency increases. Once water is captured, the job is not finished. Captured water must be removed efficiently. If it is allowed to accumulate, it becomes a secondary problem. It can be re-entrained into the airflow, it can overflow into adjacent airflow paths, or it can be carried deeper into the building envelope. So drainage is not an afterthought. It is part of the performance system itself. A louver that captures water but cannot drain it effectively will eventually fail under sustained exposure. Once droplets impact a blade, they don't simply disappear. They spread out and form a thin film of water across the surface. From that point on, the behavior of the water is governed by surface tension, gravity, and the geometry of the blade. Surface tension causes the water to cling to the surface rather than immediately falling away, while gravity drives it downward towards drainage paths. If the geometry supports this movement, the water can be effectively guided out of the system. If it doesn't, water can accumulate, pool, and eventually be reintroduced into the airflow. So the moment of impact is only the beginning. What happens next is equally important. Blade geometry is one of the most critical performance drivers. The curvature, angle, thickness, and leading edge shape all influence how air behaves as it passes through. They also determine where pressure zones form inside the louver. And importantly, they determine where droplets are likely to strike. Small changes in profile can shift performance significantly, sometimes improving water rejection, but increasing pressure drop or vice versa. So geometry is always a balancing act between airflow efficiency and water management. As air moves through the louver, it doesn't travel at a constant speed or pressure. The geometry of the blade causes the airflow to accelerate and decelerate repeatedly, and this creates localized pressure zones within the system. These pressure variations influence how the air moves, but they also influence how water behaves once it has been captured. Low pressure zones can encourage airflow to pull moisture further into the system, while higher pressure regions can assist in pushing water towards drainage paths. So internal pressure behavior is not just an airflow consideration. It directly affects water management inside the louver. Blade spacing and pitch directly control how open or restricted the system is. Tighter spaces increases the likelihood of droplet interception, improving rain defense. But it also increases resistance to airflow, which raises pressure drop. Wider spacing improves airflow efficiency, but reduces the number of interception opportunities for water. So this becomes one of the fundamental trade-offs in louver design: performance versus resistance. Depth introduces another layer of performance control. A deeper louver allows more directional changes in airflow. Each change in direction is an opportunity to separate water from air. So in general, increased depth improves potential performance. However, it also increases material use, physical footprint, and airflow resistance. So again, we see the same principle. Performance gains always come with system-level trade-offs. Multi-stage systems extend this concept further. Instead of a single set of blades, multiple rows are used, often with alternating or opposing geometries. This creates multiple separation opportunities within the same system. It also allows better control of drainage paths between stages. These systems are typically used where higher performance is required, particularly in exposed environments or critical air intake applications. Blade orientation also plays a role in how water behaves inside a system. Horizontal blades tend to rely more heavily on internal drainage channels and water capture. Vertical blades can assist in guiding water downward more directly and reducing lateral carry-through. Neither orientation is inherently superior. The correct choice depends entirely on exposure, airflow direction, and drainage strategy. Everywhere the louver sits on a performance curve. At one end, you have high airflow efficiency with minimal resistance. At the other end, you have high water rejection and increased restriction. There is no single best position on this curve, only a position that is appropriate for the application. Understanding this trade-off is essential because it explains why no louver system can maximize both airflow and water exclusion at the same time. Because performance cannot be judged visually, testing provides a controlled environment to measure behavior. It allows different systems to be compared under identical conditions, and it removes subjective interpretation from the decision-making process. Without testing, you are relying on assumptions, and as we've already established, Louvre behavior is not intuitive. There are several widely used standards for Louvre testing. These include AS-NZS 4740, BSEN 13030, and AMCA 500L. While each differs in methodology and classification systems, they all aim to simulate real-world airflow combined with rainfall under controlled conditions. This allows performance to be quantified in a repeatable way. Test results are typically expressed as water penetration rates at specific airflow velocities. It is important to understand what this actually means. These are not waterproof ratings. They are performance classifications under defined conditions. So a rating does not mean no water passes through. It means this is how much water passes under a specific test scenario. One of the most important factors in Louvre performance is velocity. As airflow increases, the kinetic energy of water droplets increases. This makes them more likely to penetrate the system rather than be captured. So performance is not fixed. It changes with airflow conditions. This is why identical louvers can behave very differently depending on where and how they are installed. As airflow velocity increases, the nature of the flow begins to change. At lower velocities, airflow is relatively smooth and predictable, but as velocity increases, the flow becomes more turbulent, with eddies and fluctuations developing within the airstream. This turbulence makes separation more difficult. It increases the likelihood that water droplets or even captured water will be carried through the system rather than be removed. So higher velocity doesn't just mean more force, it means a different type of airflow altogether, and that has a significant impact on performance. There are several common misunderstandings in interpreting Louvre data. One is assuming that high classification equals no water ingress. Another is ignoring the test velocity when comparing products. And another is directly comparing results across different standards, which are not always equivalent. All of these can lead to incorrect design decisions if context is not considered. All Louvre systems have operational limits. If airflow velocity becomes too high, or if rainfall intensity exceeds capture and drainage capacity, performance will begin to degrade. At that point, the system can no longer maintain separation. Water will pass through regardless of blade geometry. This is not a failure of design, it is a physical limitation of the system. Even when water is initially captured, it can re-enter the airflow. This is known as re-entrainment. It typically occurs when drainage is insufficient or when airflow velocities create secondary lift forces on pooled water. The water that has already been separated can be reintroduced into the system and carried further inside. Managing this is just as important as initial capture. In real buildings, conditions are far more complex than test environments. Wind direction shifts, turbulence is created by surrounding structures, pressure zones fluctuate constantly. So while test data provides a useful baseline, it does not fully define real-world performance. Actual behavior depends heavily on installation context and environmental exposure. If we step back and look at the Louvre as a whole, it can be useful to think of it as a passive air-water separation system. There are no moving parts, no active controls, and no external energy input. Everything it does is achieved through geometry and physics. This is very similar in principle to separation systems used in mechanical or industrial processes. The difference is that here it's happening in an architectural component exposed to uncontrolled environmental conditions. That perspective helps reinforce just how much engineering is involved in what appears to be a simple facade element. To bring it back to a single simple idea, if air and water behaved the same way, weather louvers wouldn't work at all. Everything we've discussed, blade geometry, spacing, depth, testing, performance, all of it depends on the fundamental difference between how air and water move. That difference is what makes separation possible, and understanding that is what allows us to design and specify louvers with confidence. To conclude, weather louvers are far more than simple architectural components. They are aerodynamic devices, water separation systems, and drainage mechanisms, all operating together in a single passive system. Their performance is governed by physics, not appearance. And understanding those physical principles is what allows better design decisions, better specification choices, and ultimately more reliable building performance in the real world. Thanks for your time.